The study of physics begins, as in fact almost all classes, the study of physics begins with what we call kinematics, the study of the description of where things are. At its root, physics is the study of the motion of objects. Before we can understand why things move the way they do, we need to describe that motion. And before we can describe motion, we need to describe where something is. It sounds pretty simple, but it's actually pretty rich. It's been a very fruitful way of looking at things for 400 years. For the near future, we'll be treating every particle as a point particle. This means that it has one location and no size. Real objects, of course, have an extent, but in many applications, it turns out we can ignore that. For example, you have a location in the room. In reality, your body occupies a region of the room, but it would be helpful to imagine that there's a point that's quote-unquote you, and the rest of your body is arrayed about it. Later in the class, we'll talk about what point is you from a physics viewpoint. All positions are relative to something. There's no such thing as absolute location. The good news is we don't need absolute location. All we need is a reference frame, also known as a coordinate system. A reference frame requires three things: an origin, the location from which all other locations are measured. It's called the point of reference, and hence we have reference frames. An axis, a line passing through the origin. We actually need one axis for each dimension of interest, but for now we'll stick to one dimension. And a direction, a choice as to which half of the line will be considered positive. The most important thing is the universe doesn't care which reference frame we pick. It's a fundamental principle of physics, in fact, that the choice of reference frame cannot affect what happens, only how we describe what happens. That being said, there's often a so-called natural reference frame in which the problem is easiest to visualize or solve. Luckily, these tend to be relatively obvious from the setup of the problem. Once we have a reference frame, we can specify the location of an object as its coordinate in that frame, which is as simple as the distance of the object from the origin. The only complication is, if the object is on the negative half of the line, its coordinate is negative. Remember that distances, by definition, are always positive. So here we're saying the coordinate can be a plus or a minus of the distance from the origin, and it's minus if what we've decided is the minus half. Here, we see two persons, Alice and Bob. The reference frame is indicated by the flag, which is the origin, and the flag points in the direction we'll consider plus, in this case, rightward. We see that Alice has a coordinate of plus 4 because she's 1, 2, 3, 4 away from the flag, and she's on the positive side. And Bob has a coordinate of minus 3 because he's 1, 2, 3 away from the flag, but he's in the negative side. It's usual to use x as the variable for the coordinate, and so to use subscripts to indicate whose person. So we would write x sub Alice is plus 4, and x sub Bob is minus 3. Honestly, we would write plus 4 meters and minus 3 meters, because we're going to be careful to keep track of units all the time. But for simplicity during this discussion, when the only units will be meters, we'll leave them out, just so we're not carrying extra symbols around. Alright, then, movement is a change in location during some time interval. So we need to talk about changes in location. The technical term is displacement. The displacement of an object between the two ends of an interval of time is simply the latter coordinate minus the earlier coordinate. We symbolize the displacement as delta x, because this triangle is the Greek letter capital delta. It's a delta and it's the capital version. And together, delta x represents the displacement. We often read delta as change in. We'll come back to that. Let's symbolize the location at the early moment as x sub earlier, and location at the later moment as x sub later. And then we have that delta x is x later minus x earlier. Notice that there is always an implicit time ordering in delta x. It's always later minus earlier. There are very old conventions that are happily fading away that use delta as just the absolute value of the difference, but we don't use that in physics ever. Like never, 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 never. Sometimes they do it in chemistry, never in physics. Delta in physics is always time ordered, later minus earlier. As an example, if Alice had started at plus 4 meters and then walked to plus 7 meters, her displacement is plus 7 meters minus plus 4 meters, or plus 3 meters. She's 3 meters further from the origin in the positive direction. Notice that displacement carries a direction, its sign. If Alice had started at plus 4 meters and walked to plus 2 meters, her displacement would be plus 2 meters minus plus 4 meters, but that's 2 minus 4, or minus 2 meters. She's walked 2 meters, but opposite to the direction we picked as positive. That's why in kinematics we often explicitly put pluses that we don't need because they are the counterpoint to minuses that we do. And so we'll use plus or minus as sort of the thing which carries the direction. And then later on when we talk about vectors, we'll generalize that pretty easily and start moving forward from there. Note the important difference between displacement and distance traveled. In the second case, Alice's displacement was minus 2 meters, but she traveled 2 meters. Why? Because distance is always a positive quantity. Really can't take that home, right? That's really important. Distance is always a positive quantity. Distance is unsigned. An important, if somewhat counterintuitive case involves a round trip. If Alice walked from plus 4 meters to plus 14 meters and then back to plus 4 meters, her distance traveled would be 20, 10 meters outward and then 10 meters back. But her displacement would be 0 meters because her final coordinate is the same as her initial coordinate, so they differ to 0. In the same vein, track stars during many races end up with 0 displacement because they run around the track, but they end up back where they started. They all run the same displacement, which is 0. It definitely sounds strange, but the distinction does have physical implications. Nature, for the most part, cares more for displacement than for total distance traveled. So, example. We have a strobe photograph, meaning in each case, a sphere is moving from left to right next to a tape marked in meters. A strobe photograph is taken every second, and the location of the sphere is recorded. The total time intervals are not the same. Total time intervals are not the same for all spheres. So for instance, we have flash, and then 1/1000 flash, 1/1000 flash, 1/1000 flash, 1/1000 flash, and so on. These kind of stroboscopes are a common way to show motion, especially in one dimension where they're relatively easy. Draw a blue circle around the case or cases with the greatest displacement during the first 2 seconds, and a red circle around the case or cases with the least. It's really crucial that you pay attention to the first 2 seconds. So for instance, if we're looking at case A, this flashes at 0 seconds, and then flashes again at 1 second, and flashes again at 2 seconds. So we want the difference between this position and this position. And that's pretty clearly 4 meters, 4 minus 0. But for part B, we have flashes at 0, and then at 1, and then at 2. And so our displacement is the difference between this position and this position, which is 1 meter. Flash at 0, flash at 1, flash at 2. We want the difference between this and this. That's very clearly 6 meters. And then flash at 0 seconds, flash at 1 second, flash at 2 seconds. That's our 2 second mark. That's our 0 second mark. So we want the difference between this position, and that is clearly 8 meters. So which one gets blue? Well, clearly this is the greatest. Which one gets red? Clearly this is the least. In this problem, each graph below shows the position of an object as a function of time. We'll talk more about this in a little bit, but we can start from here based on our current definitions. Draw a blue circle around the case or cases with the greatest displacement during the first 4 seconds, and a red circle around the case or cases with the least. Remember that the displacement, delta x, is x later minus x earlier. So here it's going to be x at 4 seconds minus x at 0 seconds. And it doesn't really matter what's happening in between them. We just take those points. So for instance, here is 4 seconds, here is 0 seconds. Hey, that difference is 0 meters. They're at the same place. We want that, which is 6, minus that, which is 2. So that's 4 meters. Here we want this, which is 0, minus this, which is 8. That's 8 meters, which, remember, is the absolute value of the minus 8 that is the displacement. It gets a little weird here because the displacement has a sign. So we come back and talk about that in a bit, whether we should use the plus or minus here. Yeah. And then the final case is There is our final position. There's our initial position, also 0 meters. So the way this is phrased, we should probably use this as our greatest, which is weird, and use this as our least, because really we should say it's -8. The displacement is -8. This probably should have been phrased differently as the greatest magnitude displacement. And that glitches on me. The other important part of motion is the time interval during which it occurs. There isn't a standard term, but I like to define the duration of a motion as the interval of time during which it happens. We measure time with a clock, of course. Much like needing an origin for a reference frame, we also need a starting point for our clock. And again, it's arbitrary and up to us. But we don't get to pick the direction. Time only flows one way. Let t sub earlier be the time on the clock when we start observing a moving object, and let t sub later be the time when we stop. The duration is then given by delta t, as delta t is t later minus t earlier. Note the reappearance of the delta. In science, delta can be read as change in, and it's always later minus earlier of whatever follows the delta. So delta x is change in x, and delta t is change in t, and delta of any quantity is the change in that quantity. Notice also that time is special. The value of t for a later moment is always greater than for an earlier moment. That's how we know it's the later moment. Later moments always have higher t values. Thus, delta t is always positive. T can be negative. That's just an event that happens before our reference time. Think about things like 20 minutes before midnight, which would be at time t equals minus 20 minutes if midnight is our reference. But delta t being positive always reflects the fact that time moves only forward. We can now talk about how quickly an object changes position. This is what we call its average velocity, v sub average. And v sub average is delta x over delta t. The average speed of something is its displacement divided by the duration of its motion. As a quick and dirty example, if a car travels 12 miles during the course of 15 minutes, what is its average velocity? V average is delta x over delta t, or 12 miles over 15 minutes, or 4/5 of a mile per minute. We might want to convert that, so we say 4/5 of a mile per minute, but every 60 minutes is 1 hour, so we can essentially cancel the minutes, and we're left with miles per hour, which is what that means. So 48 miles per hour, 4/5 of 60. If the displacement is negative, then the average velocity will be negative as well. That again comes back from that v average is delta x over delta t, and delta t cannot be negative. It is always a positive quantity, and therefore the sign of v is just controlled by the sign of delta x. As an example, what is the average velocity of a cart that starts at plus 2 meters and then 4 seconds later passes minus 3 meters? So we put v average is delta x over delta t, or minus 3 meters, the end, minus the initial, which is 2, over 4 seconds, which is minus 5/4 meters per second. Often we don't care which way a thing is headed, only how fast it's moving. This is something we call its speed. For instance, if you're going to get a ticket from the police officer, they don't care which way you're headed. They only care how fast you're getting there. Speed is really easy, though. It's just the absolute value of the velocity. So the average speed is the absolute value of v average for our existing guy. Oh, sorry. Typo. This should have been minus 5/4. So 5/4 meters per second. Just simple typo, kind of silly. All right, here's a motion diagram of a car which is moving along a straight road. Which position versus time graph could match the motion in this diagram? So we look and we say each of these dots is occurring at some fixed amount of time. Flash, 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 flash. And we can see that during these time intervals, although the time interval is the same, the delta x is less, so the v will be less. It doesn't cover very much distance. Whereas over here, it covers a lot of distance, so the v is more. And we can see that this ends up being this one. We've mentioned graphs a couple of times. Let's talk about a graphical interpretation. Consider a toy car moving rightward at a constant velocity of plus 2 meters per second. As it passes the origin, we start our stopwatch, so it's at x equals 0 when t equals 0. In the first second, it travels 2 meters, and so it's at x equals 2 meters when t equals 1 second. And the next second, it travels another 2 meters, so it's at 4 meters. The second after that, it travels another 2 meters, and it's at 6 meters. We could make a table of these values as indicated here. It's always suggestive to graph the data table. So we take that data and we throw it onto a graph where on one axis we have the position of the thing, and on the horizontal axis we have the time at which it is at that position. And then we make these dots and we see this thing. This is what's called a position plot, sometimes called an XT plot. It's maybe the fundamental type that we'll come back to over and over again. It's a way of quickly characterizing the motion of something, and here we see something interesting. This XT plot is a line. One of the introduced feature of lines from algebra is their slope. We pick any 2 points on the line and calculate the rise over run. For no good reason at all, I've decided to pick these two values. Notice they are not any of our given values. They're the things on the line, not our data set. And then we just compute slope, which is rise over run, which is 8.5 meters minus 3 meters over the 4.25 seconds minus 1.5 seconds. And we get, in the end, 2 meters per second, which is the velocity we started with. And that's not a surprise, because, of course, rise over run, on the XT plot, it's the change in the vertical coordinate over the change in the horizontal coordinate, so it is going to be the average velocity. And that's kind of useful and neat. This turns out to be true in general. Given an XT plot, the average velocity during interval is always the slope of the line connecting the start and end of that interval, even if the graph is not a line. And to stress on this, the average velocity is always the slope of the line connecting. Consider the weird graph to the right. This is an object that moves rightward, it stops, it moves leftward for a bit, and eventually winds up to the left of the origin. We can compute its average velocity between, for instance, 1 and 2.5 seconds, those values chosen more or less randomly, by connecting those points and calculating the slope. Since we're reading from the graph, of course, the answer would be approximate, but during the time interval shown, between 1 and 2.5 seconds, the average velocity is minus 1.1 meters per second. We'll see later the velocity is never equal to that value except maybe at one location in here, but in general is not equal to that value, but on average it comes out to that value. And we'll need to do a little bit more pre-calculus or proto-calculus to come back and talk about that, but it will be important when the graph is not linear, how to interpret it. And that's something for the next time.